Our next topic on applying the derivatives is called linear approximation. This is something you actually already know how to do. We're going to kind of formalize it and talk about some words that you haven't seen before. But what it is basically is you're going to write the equation of a line tangent to a graph at a very close point, and then you're going to use that line to approximate what might be happening, to give an approximate value. Like, for instance, if we know that the square root of 9 is 3, then the square root of 9.1 is a little bit more than 3. Well, what linear approximation using our differentials will do is tell you, well, just how close is it to 3? So we'll get a pretty good estimate. So here we go. If you have something like y equals f of x, with the function f being differentiable, at a particular point, then you can approximate the differential by going, or the linear approximation, f of x would equal what they call, or approximately equal, L of x, the linear approximation, which is my f of x sub 0, or x naught, my original value, plus the derivative at the original value, times the change in the y values, so y minus y sub 0. Excuse me, x minus x sub 0, the change in the x values, for all x values near the original value. So for instance, if I got further and further away from 9, let's say I was approximating 9.1, I'd be pretty close, but if I was trying to approximate 10, I'd be further away from the approximation. So say we have something like this. Say we want to approximate the square root of 17 by using the point that's near that, which would be the point 16, y value of 4, on the graph of y equals the square root of x. So what we want to do is we want to write the linear approximation of the function for y equals the square root of x at the point 16, 4. So you already know how to do this. This is from before. First of all, find the derivative. Y prime is 1 over 2 square root of x. If I plug in 16 right there, I find the slope to be 1/8. So then the linear approximation would be y minus 4 equals 1/8 times x minus 16. Now, if I wanted to use this line to approximate the square root of 17, what I would do is I would put in 17. So L of 17 would be, move that 4 over, 4 plus 1/8 times 17 minus 16, or 4 1/8. That's 4.125 on your calculator. That's going to become a very close approximation to what the square root of 17 is. The second part, the part that's the derivative times the change in the x value, has a special name. It's called a differential. The differential are oftentimes used to see how much greater or smaller a particular value is than what actually the target value is. So if we let y equals f of x, where f is differentiable, function, the differential, what we call dy, which is an approximation of what delta y is, it's an approximate change in the y value, the derivative at x times the change in the x value. It's that second part of the linear approximation I gave you just a moment ago. We use this much more often than we find the exact value of the change in y, because finding delta y, finding the exact change in y, is often very difficult. Approximating dy is often much easier. And combined with this, and I'll do an example in just a moment, but combined with this, we're going to talk about error. So let me just get error in there for a second, because we got to talk about how close are we. You know, is it close enough or is it not? So first of all, we deal with absolute error, and the exact value for the absolute error is delta y, and that's going to be y sub 1 minus y sub 0. The approximation of that is going to be dy, which remember is f prime of x times delta x. Once you know the absolute error, you can find the relative error. The relative error just means, okay, well, how much are you off based on what the original measurement is? So, for instance, if you were if you're measuring something, let's say you're working on a construction project on the highway, and you're looking for seams in the road, and let's say you're off by 1 inch. Is that a big error? Or is it a small error? Well, you know what? If you're paving, hundreds and hundreds of feet of pavement, 1 inch is a pretty small error. But if you're 1 inch off and you're making an iPhone, that would be a huge error. So it's a relative error is going to be the absolute error over the expected value. And the approximation of that would just be dy over y. And then we can talk about percent error. And the percent error is that relative error times 100. So delta y over y sub 0 times 100. Or dy over y sub 0 times 100. Get it in percent range. Okay. This error stuff is not stuff that you'll have on the AP exam, but I will test you on it. It's something you should know. So we'll get into that a little bit. I'll do an example of that later on in the notes here. The next part, let me just go to dy and delta y, and why we use dy as opposed to delta y. It's a lot easier. Let's say we have y equals 3x squared minus 5. And I want to evaluate two things. I want to find I want to find dy, which is the approximation of delta y. That's going to be the easy one. And then I want to find delta y. And I'm going to compare those values. So dy, remember, is the derivative of f of x, so f prime of x times delta x. And this particular example, that's going to be 6x times delta x. Not hard to find. However, if you want to find the change in y, if you want to find the delta y value, exactly what you're going to have to do is you're going to have to evaluate this. You're going to have to evaluate f of x plus delta x, how much you're going up by, minus f of x, the original function. So this is the second y value, that's your original y value. If I plug in my numbers, it's 3 times x plus delta x. I'm just putting in my equation here. Quantity squared minus 5 minus my original equation. Let me clean this up a little bit. Minus 5 minus 3x minus 5. 3x squared minus 5. Algebraically, what I want to do is I want to square out that first binomial. So just continuing on with this, it's going to be 3 times x squared plus 2x delta x plus delta x squared minus 5 minus 3x squared if I distribute that negative plus 5. And what ends up happening if I distribute the 3 here, combine my like terms and clean it all up, I get 6x delta x plus delta x squared. And now this goes back to something I talked about just a few minutes ago when I said that the differentials or the linear approximation is a good approximation provided that the x value, the change in the x value is very small. If it gets larger and larger, then this part right here, which is the difference between this and dy, notice the difference between this equation and this equation, that difference is just that delta x, and I'm squaring it. So if this number, if delta x is very small, then these two are essentially the same. If delta x gets larger and larger, then these become further and further apart. Let's say I want to use differentials to approximate y equals the sine of x. If x changes from pi over 3 to something very close to it, let's say 61 pi over 180. Remember, 60 pi over 180 is pi over 3. First of all, y prime is cosine of x. The linear approximation would be my original equation, sine of x at pi over 3, which is square root of 3 over 2. And it's going to be then plus the derivative at pi over 3, which is 1/2, cosine of pi over 3 is 1/2, times x minus pi over 3. If I were to plug in my values there, if I plug in 61 pi over 180 right here, what ends up happening is I end up with the linear approximation of 61 pi over 180. And remember, in our class, everything has to be in radians. It's going to be square root of 3 over 2. And then it's going to be plus pi over 360 if I put 61 pi over 180 in there. Okay. We'll get a little bit more into the air stuff in class. We'll talk about that a little bit more and just kind of make sure that you're very clear about that. Okay. So good luck on that first part of linear approximations, and I'll do a couple of air examples in my next video.